Hi everybody, I'm just finishing up an example I didn't get to at the end of class today. Okay, so here we are looking at a rational expression, and our goal is to rewrite this in a way that we can actually take an integral of it. And we know that the denominator is not a reducible, it's an irreducible quadratic. You can check this. B squared minus 4 times A times C is going to be a negative number. So how can we integrate something where the denominator is an irreducible quadratic? Well, we saw before that if we can get the denominator to look something like a variable squared plus, plus a constant, then we can integrate it using either u substitution with the numerator, or we can integrate it as an inverse tangent. So this is what we're going to be trying for. We're going to try to get a variable squared plus a constant here in the denominator. And our process for this is going to be to use completing the square. I'm going to copy out the denominator on its own, x squared plus 4x, and then I'm going to separate out plus 13. Now, my goal is to make the part inside of the parentheses here into a perfect square trinomial. So I look at the coefficient here on the b. We want to divide that number by 2 and then square the result to figure out what constant needs to be added in here. So 4 over 2, the quantity squared. 4 over 2 is 2. 2 squared is 4. So I need to add a 4 inside of the parentheses. But to keep these actually equal to each other, to actually use this equality sign, I have to take that 4 away outside of the parentheses to balance it out. So here we're adding 4 and subtracting 4. That cancels each other out. So now I can rewrite the part inside of the parentheses here as something squared. This is the perfect square trinomial x plus 2, the quantity squared. And negative 4 plus 13 is 9. So now, if I look at what I've got here, I've got an expression using our variable x that's being squared, and then added to that, I have a constant, which is essentially what I need, except that I want this x plus 2 here to be just a single variable. So in order to make that happen, I literally just make that happen. Assign a new variable to be equal to x plus 2. Call it u. Now du is just dx in this case, and we would be able to use that if we were looking at the integral of this whole thing, dx, right? The numerator here also needs to be changed into being in terms of u, because we're getting u squared plus 9 in the denominator here. To get the numerator in terms of u, we just have to solve this equation for x. So if u is equal to x plus 2, then x is equal to u minus 2. So this whole expression here can be rewritten as the integral of u minus 2 divided by u squared plus 9 dx. And now, just like in our previous examples, when we have a denominator that we like, all we have to do is split up our numerator over addition or subtraction. So this is going to become the integral of u over u squared plus 9 du, oops, sorry, that should have been a du as well, minus 2 times the integral of 1 over u squared plus 9 du. Now for the first one, we can do a quick substitution in order to rewrite this as an integral that we can actually take. The numerator is like the, it's like the derivative of the denominator here. So we need a new variable. We've already used u, we better use w. So we get w is equal to u squared plus 9. And therefore dw is equal to 2u du. And I have a u du, so I'm just going to divide 2 on both sides so that I got that set up. Okay. Now to continue, to continue, we're going to recopy these integrals here. So we have the integral of 1 over w. So 1 over the u squared plus 9 becomes 1 over w. And then the u du becomes dw over 2. And then we have minus 2 times this integral here of 1 over u squared plus 9 du. Okay, so now we can integrate both of these using what we know from our previous examples. The 1 over 2 part here can just be factored out, so we have a 1/2. And then the 1 over w, the antiderivative of 1 over w, is going to be the natural log of the absolute value of w. Here we have minus 2 times, and then this again looks like an example we looked at earlier in class. We have 1 over a variable squared plus a constant that's not equal to 1. So you can go through that quick substitution process again. You would need yet another variable, so you would call it t this time. T is then equal to, say, u over 3, so that u is equal to 3t, and u squared plus 9 is equal to 9t squared plus 9, so that you can factor that 9 out, right? That's the idea there. But if you don't go through this process, you can see probably, I hope, that this 1/9 is getting factored out here, and we get a 1/3 factor here going on. So this is going to be minus 2 times the inverse tangent or the arctangent, whichever you like, over 9, so 2 over 9, arctangent or inverse tangent of t or u over 3. And then we have plus our constant of integration here. Now we're still not done. We are trying to take an antiderivative here. That's our goal from the beginning. And our original function was given in terms of x. So we need to get our final answers here also back in terms of x. What I just erased said that u is equal to x plus 2. That's important. So now we're going to work our way back. We know that u is equal to x plus 2, and we know that w is equal to u squared plus 9. So we can fill in what we need to know here in terms of the variable x instead. So we get 1/2 times the natural log of the absolute value of w, which is u squared plus 9, which means x plus 2 squared plus 9. And then we have minus 2/9, the inverse tangent of, and then instead of u over 3, we'll have x plus 2 over 3. Plus our constant of integration. All right, and you might have noticed, by the way, that this expression here inside the absolute value, is precisely equal to the denominator here. So if you like, you can finally write your answer involving the original fraction here. 1/2 the natural log of the absolute value of x squared plus 4x plus 13 minus 2/9 the inverse tangent of x plus 2 over 3 plus our constant of integration. There we go. And if you want to go even a step further, there's like tiny little simplifications going on here. You might notice that this number inside of the absolute values here is always going to be positive. You could graph this function and show yourself that as well, that all of the y values of this function would then be above the x-axis. You could notice that here we're taking a number, doesn't matter what that number is, and squaring it to make it a non-negative, and we're adding 9 to the result. It's definitely a positive number when we're done. So the absolute values aren't changing anything here, so if you really like, you can write it one more time, or you can just like that. The absolute values are not necessary, just parentheses. Okay, so that's how you use completing the square to rewrite a denominator into a form that we actually can use to take the antiderivative. And then you can see the process from there to write the final antiderivative for the original function. And once again, you can always check your work. In order to check your work, you need to take a derivative of this last part here. And then you'll probably need to work with manipulating fractions around until you get back to the original. But it is possible to check. All right, so that's the end of this example here. I'll be posting this alongside the class video for today. Sorry again for running out so early.